So the following presentation, it is by Chris. Is Chris here? Okay. Polymer success stories and future challenges in the area of sustainable development. So if you catch the idea, we have each field of science in the perspective of their application into the framework of sustainable development. Challenges, successes, challenging, and the future of each of the fields in the era of sustainable development. Yes. The floor is yours.
Thank you very much, Florian. It's a really great pleasure and honor to be here and to listen to many plenary lectures, but also more topical lectures. And in fact, this title was designed not by me, but by Florian. So he wanted me to tell you how it really happens that polymers are becoming so important in our world, and how we can make them better, how we can design them in a better way. So I probably would like to start with a graph very similar to what Professor Marquis was showing, but this relates to really trends in steel, so this is this blue line, and also in polymers, the red line. And this is done on the same scale by volume, not by weight. And you could see that polymers practically did not exist as a significant material in the time before 1950, and this was more or less the time when I was born. And in 2000, more or less, the volume of polymers exceeds significantly steel, but we could see what happened in the last years. Now we have 400 million tons of polymers per year. So this is 400 billion kilograms per year. Divided by 8 billion people, it means it would be approximately 1 kilo per week per every person. So it's a really amazing amount of polymers and the growth as well. I marked also this 1967 because it was the time when I was essentially deciding what I should do in the future. And also it was a year, a very remarkable movie was produced. It was The Graduate. I don't know how many of you have seen this movie. This was one of the best movies I have ever seen. And this is with Dustin Hoffman and also Anne Bancroft and some others. And there is a really very important message from this movie. I will play a short clip, and this is when... okay.
Okay,
Just
perfect.
one word.
Yes, sir.
Are you listening?
Yes, I am.
Plastics.
Exactly how do you mean?
There's a great future in plastics. Think about it. Will you think about it?
Yes, I will.
Enough said. That's a deal.
Here he is now.
So, in fact, I followed this advice, and I decided to learn something about plastics and how important they are. We heard from the previous speakers already some examples why plastics are used, or sometimes composite materials. First, because they are much lighter than steel. So because of that, either in the airplanes, like we heard about Dreamliners, or in cars, you use much less energy because they are just lighter. Also, they are very easy to process. You can process them not like metals at 1,000 degrees, but sometimes essentially at room temperature. And also they are not corrosive. So they can stay and cars do not rust anymore. And there are many advantages. Sometimes also it's a challenge because you will accumulate these polymers and it's a question of pollution and how you can degrade polymers, how you can depolymerize polymers back to monomers. This is something which I will tell you at the very end. So unfortunately, there are many polymers which are used for just packaging only, but sometimes for very high advanced materials, some polymers are stronger than steel. Example would be Kevlar, but also ultra-high molecular weight polyethylene. Without polymers, there would be practically no computers, no integrated circuits, no electronics. You need photosensitive polymers to do that. And very interesting possibility, which I will also briefly tell you, is about polymers in biomedicine. When you think about a COVID, we won this war with COVID because of the polymers, which would be used for delivery, sometimes also for simply protective gear. And very interesting would be really materials which would target, sometimes with antibodies or some targeting devices, particular parts of the body or tissue. So if you have a cancer, people take sometimes chemotherapy or radiotherapy, and you kill many healthy cells, not only cancer cells. So how we can do it better? But I probably should say that these are examples of synthetic polymers, but there are also natural polymers. These natural polymers, such as cellulose and starch, we just eat. And in fact, our bodies, is 70% water, and the rest are polymers. It would be proteins, working horses, essentially, of our bodies, but also nucleic acids, responsible for our genetic heritage, also for our dreams and love. Without polymers, we simply will not exist. So how to make polymers? So there are really two ways in general. This is like a course in polymer chemistry on one slide. One way is to use so-called step growth reaction. When you think making proteins, it will be reaction of amino acids. So you have an amino group, and you have also the carboxylic acid group. So if you take amino acid, you can sometimes make protein, but you can also make nylons, exactly in the same way. Reactivity of this group A, let's say amino group, in a monomer, and in a dimer, in a trimer, tetramer, is exactly the same. Because of that, the molecular weight or degree of polymerization increases very slowly with conversion. It follows so-called Carver's equation, and this X means conversion. So if you go to 50% conversion, you get only dimer. If you go to 90% conversion, this X would be 0.9, you will get a decamer. So in order to get a polymer with degree of polymerization, roughly speaking 100, you need to go to 99% conversion. This is a challenge. It takes time, it takes energy. So how else we can make polymers? So alternatively, you have a chain growth reactions. So in a chain growth reaction, monomer does not react with a monomer. You can have a styrene or methyl methacrylate or ethylene by itself. It would stay practically forever until it is initiated. It can be initiated by sometimes acid, base, by organometallic species, like in Ziegler-Natta polymerization, but also by radicals. And I will tell you a little bit more about radicals, but really the propagation is very, very fast here. Sometimes monomer adds to a chain end with a frequency of 1 millisecond, or sometimes 1 microsecond. So very quickly, you build up very high molecular weight, but then you have some chain breaking reactions, transfer and termination, and molar mass drops with conversion. Very difficult to control these reactions. So 60 years ago, Michael Schwartz developed so-called living polymerization. Living polymerization is without transfer, without termination. So if you have a ratio of monomer to initiator concentration 100 to 1, if you go to 50% conversion, not degree of polymerization 2, but 50. You go to 80% conversion, 80, 100, 100. And then if you add more monomer, it continues to grow. So it's a living polymerization. But if you add another monomer, you make a block of polymer. And this was a revolution in polymer science, because polymers hate one another. They cannot really be together. They phase separate, but if you connect them covalently, in that case, they phase separate on a size of molecules, on nanoscale. So this was the beginning of nanotechnology, making materials of a size of domains 5 nanometers, 10 nanometers, with a very regular structure. So in that case, this X is not anymore conversion, it is selectivity. It means how many times you propagate before these chain-breaking reactions happen. So this is really beginning of the macromolecular engineering, materials which would be really prepared in a tailor-made way. So I mentioned to you that in a radical polymerization, why we decided to look at radicals, because they are very tolerant to many impurities, but also to many functional groups. They can be combined with proteins, with nucleic acids, making bioconjugates, linking polymer to protein or to nucleic acid. But the challenge in a conventional radical process was that after 1,000 monomer addition, after 1 second, there was a termination event. You could not make these materials anymore. So it was necessary to extend life of growing chain from a second to minutes, hours, or days. And we do that by equilibrating these radicals with so-called dormant species. Dormant means sleeping. They cannot propagate, but they cannot terminate. You need to wake them up by using some kind of a catalytic system, consisting of the activator and deactivator. Activator is responsible of making radicals. Deactivators, after 1 millisecond activity, going back to a dormant state. So we developed catalysts which are now 1 billion times more active than originally used. So we can use them at very low concentration under green chemistry conditions using parts per million of copper. But we cannot completely suppress termination, so we need to remember that every act of termination will convert these parts per million of activators to deactivators. Reaction would stop. We need to regenerate these activators using various mild reducing agents, something like these antioxidants, which we heard in the first or second lecture. For example, vitamin C, or sometimes sugars, sometimes electrical current, or light. And also, we develop systems which are air tolerant. Normally, oxygen, triplet oxygen, kills growing radicals. We develop techniques which can overcome this problem. So this opens possibility to make polymers, but also very sophisticated structure, like these bioconjugates, or decorating nanoparticles with polymers, or putting 10 nanometers layer on a surface of whatever material you have. And these 10 nanometers will make material surface antimicrobial, or anti-fouling, or super lubricious, and change dramatically properties, having only less than 1% or 0.1% by weight of the entire material. So this is really relevant. We have 18 industrial commercial licenses, and we have over 60 industrial consortium members learning how to make these materials in a future. So the next slide. So this really shows you what you can do with the corresponding macromolecular architecture or engineering. Sometimes you can make linear polymers, long polymer chains, but you can make also cyclic material. You can make star-like polymers. You can make comb-like polymers, or networks with precisely controlled architecture. If you have more than one monomer, you can make statistical copolymers, but you can make also block copolymers, those which would phase separate to these nanomorphological structures. Or you can make a sequence control or gradient, and also put many functionalities. So you could see here some examples of molecules which would be pom-pom-like, or mictoarm star, or molecular brushes. And it's very easy to essentially draw these structures, but how can you prove that you make them? So here is an example. So this is an example of a molecular brush. And this brush is made by backbone of methacrylate, having 400 repeating units. And every repeating unit is a quarter nanometer distance in a fully extended chain. So this is approximately 100 nanometers long molecule. And then every repeating unit has a side chain of polybutyl acrylate. And because of that, you could really image this material by using atomic force microscopy. You can count how many side chains you make. They are called as bottle brushes because they are extremely densely grafted. Every quarter nanometer is a one side chain. And they have sometimes amazing properties because polybutyl acrylate is very, very soft. It has a glass transition minus 50 degrees, so it's a liquid. If you put them on a surface of mica, they stick to mica. But if you put them on a surface of the if you put them on a surface of graphite, you could see these molecules moving. They are dancing, essentially, to this bolero by Ravel, and you can see what happens in this case. These molecules, you will see probably first time in your life, maybe, molecules moving as such. So they are large enough to be observed or imaged by the corresponding atomic force microscopy. So can we go to the next slide? So one important issue is the mechanical properties. So every polymer below glass transition is glassy. So it is like plexiglass or polystyrene. It has a moduli in a range of 1 gigapascal. So it would be like this counter table here. But if you go above glass transition, they become much softer. And eventually, they become really like a rubbery material. If you cross-link them, typical rubber, if you think about rubber band in your fingers, it would have a modulus in a range of 100 kilopascal. But our bottle brushes are very short. They cannot entangle, so they relax further on, and they reach super soft rubber properties. So they are 100 times softer than rubber. So when you think, what materials do you know which are 100 times softer than rubber? Not many. So this would be something like a jelly or hydrogel. But hydrogel is 99% water, 1% polymer. When water evaporates, hydrogel becomes very hard. So that's why you cannot use them in contact lenses or any other applications, because they would hurt you unless you keep this lubricant like water constantly there. So can we make a material as soft as hydrogel, but which would never evaporate? Material which would be always super soft. So we tried to make them, and let's go to the next slide. And you could see these images of the polybutyl acrylate side chains with a backbone around 2000. So they are, roughly speaking, half a micron long. And you could see what happens if I grow a longer side chain, 17, 23, 34, 130. They are becoming more stretched. And also, if you go to the next slide, you could see how it affects mechanical properties. Next slide. So you could see that there was a prediction made that modulus, or stiffness of the material, should scale with a power negative 1.5 with the length of a side chain. So we go with a longer and longer side chain, 4, 17, 23, 34, 130. At 130, we get a modulus 200 Pascal. So they are not 100 times softer than rubber, they are 1,000 times softer than rubber. They have really amazing properties and maybe I can try to do it myself. Yes. So you could see here what happens. If I take a hydrogel, this is 10% polymer, 90% water. This is polymer backbone, 8%, 90% side chains. So when you press them, you could see that this reversibly can recover all properties and is this super soft material, and this hydrogel is much more brittle. So you need to design these materials properly, because it's not only length of a side chain, but also distance between these side chains. If you have a too short distance, sometimes they become really unbrittled as well. So you can design them by using these two, or you will see later by three properties. So what they are used for? So this is an example of a material made by Kaneka Corporation in Japan. And you could see it's like a 1 inch thick layer. It was a raw Japanese egg, and you could see that it survived. And if you would go to a bit more ambitious, this is Dr. Yoshiki Nakagawa on a 3rd floor, and you could see that he can drop the egg from the height of 10 meters or maybe more, and still this thing survives. So what can be used for? One example is really shown here to transport very delicate things on a rough surface. You could see if you use the polymer here, which would be like a pad of 1 inch maybe size, which would isolate all of this vibration. And in that case, this is what happens without this vibration isolator and what happens with vibration isolator. Dramatic change. You could see here what happens without isolator and with isolator. And you can do the same with sometimes also glass or metal bearings without and with isolator. And you can even quantify that by moving this card on a rough surface. You could see oscillation which are coming with and without isolator. And now you can transport these goods in a much more efficient way. Now I wanted to show you one maybe a little bit less okay, can we go to the next one? Okay, it's fine. All right, we probably can skip the next. Oh, once you start it. Let's go to the next slide. Next one. Okay. So, in fact, these materials are very soft, but also you need to cross-link them. So we have 3 parameters. This would be length of a side chain, this would be grafting density, and then cross-linking density. So these 3 parameters are nearly like a genetic code for this material, and you would like to make them very similar to tissue. Tissue has very different properties than typical polymers because they can be either rigid but also brittle. Anything which would be including even carbon fibers, they would behave in such a way. Or you may have very rubbery material, extremely soft. I showed you even this super soft material. But we can have also tissue which have a so-called strain hardening. So can we reproduce such behavior in polymers? For example, if you take a dog lung, in that case, you will see this strain hardening, and then through some artificial intelligence and machine learning, we can fit this analysis and convert them into these 3 parameters: length of a side chain, grafting density, and cross-linking density. So you could see here, if we design it in a proper way, we can mimic the alginate gel, we can mimic jellyfish, we can mimic artery or even lung. And you can go even to a softness of brain. So how we can incorporate them into bodies? One way would be to really think, this is an example of a skin. This is what would happen without strain hardening, and this is what happens with strain hardening. So how can we inject them? You make this very soft center part, which is water soluble, and then here is a part of a smart polymer. Smart, it means that it will go through a phase transition. It is on one side very water soluble at temperatures below body temperature, below 30 degrees. But if it reaches body temperature, in that case becomes insoluble and gets really pseudo cross-linked, physically cross-linked. And now you could see that by proper design, you can mimic property of a muscle, of a brain, of even fat. So extremely soft materials. So let me switch now to an example of some new design drugs. If you look at the 2 years ago, the market of some drugs, this is still during the COVID time, this one and this one, and all of these red highlighted drugs, they are practically based on conjugates, either with polymers or with antibodies. And this is huge market. So each of these drugs is billions of dollars. So why they are so really important and so successful? One example is shown here by the drug which Amgen introduced 20 years ago called Neulasta. It is based on a protein, filgrastim, which is used when people take a chemotherapy. There is imbalance of white blood cells, and with this filgrastim, it is coming back to a normal. However, when you inject this filgrastim, which has a molar mass, 19,000, into body, it is cleared after 2 hours through kidneys. So you need to inject it again and again and again, every 2 hours. So what they did, they conjugated this filgrastim with polyethylene oxide, 20,000. Now it has a 40,000 molar mass and is not cleared through the kidneys and can circulate in a body for 3 weeks. So if you compare every 2 hours or every 3 weeks, obviously people would prefer the second option, and therefore you could see that already 10 years ago, it was a market of $5 billion. So how to make these bioconjugates? How can you make it? So what they did in Amgen or any other bioconjugates, they were taking protein with some functional groups, and then it was polyethylene oxide with a complementary group in order to conjugate them together. This was done under very high dilution to prevent aggregation of proteins, so it took a long time, and one needs to use large excess of this polyethylene oxide. So this is 20,000, 20,000, 10 times or maybe 100 times excess. How to separate them? Very, very difficult. Therefore, it costs a lot of money. Alternatively, you can put functional group, this atom transfer radical polymerization initiator, and then you add monomer catalyst, and you grow practically the same polymer. And then by dialysis, you remove catalyst and reactive monomer. So this is much more feasible and much more easier reaction. And also you can conjugate in a similar way nucleic acids with a DNA or RNA. You can make a polyplexes. You can conjugate practically with any kind of a biomolecule. So you could see here what happens if you decorate this protein with an armor of a polymer layer. First, they will become isolating or immunoisolating because antibodies cannot detect this foreign body. And in that case, it survives for much longer time. And you can run the reaction in organic solvents because enzymes are so fantastic catalysts, but sometimes they denature in the environment, which is in fact very unfriendly, and they unfold. This polymer layer helps to refold them back to original structure. So these are some possibilities, but we extend that to materials which we heard from a previous lecture, to composites. So we can decorate the surface of a flat or cylindrical like nanotube, but also spherical structure with a polymer of a variable density, and then you can make very regular material. Sometimes they behave like photonic crystals. And another possibility would be to think about materials for the future which would be self-healing. This is development of Professor Marek Urban from several years ago, which you could see if you scratch polymer surface, then spontaneously, after a couple hours, it self-heals. So this would be self-healing or self-repairing materials, or maybe self-reproducing materials in the future. So let me switch to the last topic, which is based on recycling. I think we have many politicians here which should establish right legislature, but what we as a chemist can do in order to recycle polymers. So you have to realize that making polymers is a challenge, especially entropically, because entropy would disfavor polymerization, because you need to put all of these molecules together to make polymer chain. So how can you make polymers? You need to compensate this loss of entropy with an enthalpy, either ring strain when you open a monomer, or converting double bond to single bond. And you have to realize also that if you make a polymer, for example, you take ethylene oxide, make polyethylene oxide, it is not thermodynamic product. Thermodynamic product would be 1,4-dioxane, which is toxic. So we can, by selecting the right mechanism, we can prevent this 1,4-dioxane formation using anionic rather than cationic polymerization. Or if you wish, if we have here ethylene, this is polyethylene, thermodynamic product is cyclohexane. We don't know how to, at room temperature, convert polyethylene to cyclohexane, but maybe some of you will develop in the future, and it would dramatically change what happens with the polyolefin markets. So one example is shown here, which is, okay, I think I need your help again. Next slide, please. If you take polymethyl methacrylate, plexiglass, plexiglass can be converted back to monomers at temperatures in a range of 400, 500 degrees. So can we do it at lower temperature? Can we do it through this living polymerization? And in that case, you can depolymerize polymethyl methacrylate back to methyl methacrylate and make new polymers again. So here's an example of taking this polymethyl methacrylate and exposing that to 170 degrees, not 500 degrees. And in that case, you could see that you can get a methyl methacrylate with 95% purity in the presence of iron filings, just iron powder. Or you can take a bulk polymethyl methacrylate, 180 degrees, and 80% depolymerization in 15 minutes, and high purity monomer. Another possibility is shown here by using combination of light and the heat, and you can make methyl methacrylate or some other methacrylates. And very recently, it was a paper published by Professor Anastasaki taking commercial polymethyl methacrylate with different colors. And you could see that you can regenerate methyl methacrylate with a very high efficiency. So because my time is nearly over, I would like to summarize what can we do with this polymer synthesis with macromolecular engineering. On one side, we need to understand how these things work, which means mechanistic deep understanding and also catalysis. How we can make these systems more green, robust, how we can work in water, how we can work in the presence of oxygen. But once we know that, then it would be next layer, controlling polymer composition. It would be like a sequence control in proteins. Can it be done in the future? Can we control topologies? I showed you that these comb-like polymers are super soft. But can we have also degradable polymers and more complex architecture? And of course, the next layer is what they are good for, what kind of application you have. Drug delivery systems, making these super soft materials, which I told you, self-healing materials, materials for carbon dioxide capture, electronic materials, and some others. So I think that was message to you that we can, but by using these tools of macromolecular engineering, which means we design, we make something, and then we process it and find very unusual new applications, super soft, super hard, smart polymers, which change with external stimuli, whether it is a light, whether it is magnetic force, electrical field, or something else. Thank you very much.
Thank you very much. We really appreciate. Excellent. We should invite you for another time, a similar one.